What's up, everybody? Hopefully you've already learned the chain rule. If you haven't watched the chain rule video that I have, don't check out this video. But this video is how we could use the chain rule within the product or quotient rules, which actually makes for some very difficult problems. But it's not difficult because of the derivative rules. It's difficult because of the algebra that it takes to clean it up and simplify it. So let's just dive right into a couple of examples. So here's an example of a product rule that's going to require the chain rule. So we have a function here that is made up of a function 3x cubed plus 1 times a separate function negative 4x squared minus 3 raised to the 4. So perfect opportunity to use the product rule. We have something times something else. Now, briefly, just to quickly recap on the how we actually utilize the product rule. That is, if you have a function that is something times something, right? I'm just going to say a times b. To find the derivative of this function, you take a, multiply by the derivative of b, plus b times the derivative of a. Those are supposed to be primes. There you go, b prime, a prime. Okay, that's a pretty simple rule, but now we got to apply it to this somewhat complicated function. And this back part right here, at some point we are going to have to find the derivative of this, which is going to require the chain rule, which is why we're going to use the chain rule within the product rule. So here we go. Here is me using the product rule. So first, I'm taking a, leaving it completely alone. So that is this first part right here, 3x cubed plus 1, doesn't change at all. And I'm going to multiply by the derivative of this back part. That is, of course, going to require the chain rule. So notice what happens here. The 4 fell down in front. My new power is a 3, and I left the inside alone, but I'm not done yet finding the derivative, because in the chain rule says don't forget to multiply by the derivative of the inside, and the derivative of the inside is negative 8x. So now I'm done with that first part, again taking a times the derivative of b. Now I got to go to the back. This time I'm going to leave the back part alone. Right? There it is, negative 4x squared minus 3 to the 4th, left completely alone. And I'm going to multiply by the derivative of the front part, the derivative of a in this case. 3 falls down in front, makes a 9. New power is 2. The derivative of 1 is 0. So there's my derivative right there of that first part a. So this is b times the derivative of a prime. All right, that's actually it. I am 100% done with the product rule. And again, the big part I want you to see is how I use the chain rule right here inside of the product rule. Now, I got to be honest, the most difficult part, the tricky part, comes with simplifying this. So the first thing I did was I said, all right, let me multiply what I can in each term. Again, the terms are anything separated by this plus sign. So I do have two terms, one on the left and one on the right of the plus sign. So on the left-hand side, I was able to do some multiplication. Let me quickly go back here and show you the multiplication I was able to do. I was able to take the 4 right here multiplied by the negative 8x. That made a negative 32x. I then took that negative 32 and I was able to multiply it here. Now, because there's a power of 1 right here, even though we don't write it, I'm able to distribute that negative 32x into that 3x cubed plus 1. But I am not able to distribute right here because I have a power right there. When you have that power of 3 right here, I can't distribute into that. You can only distribute it into a expression if it has a power of 1. So, and then that's how I got that. And I'll show you that work in 1 second. But then back here, the only thing I did back here is, again, I cannot multiply anything here because the negative 4x squared minus 3 is raised to the 4th. So I just moved the 9x squared to the front just because, well, to be honest, I don't know. It just kind of looked nicer. So in the back, here is me moving that 9x squared to the front times the negative 4x squared minus 3 to the 4th. And then again, I was able to multiply that negative 8x by the 4, which got me that negative 32x. And then I was able to distribute this across here, which gave me a negative 96x to the 4th minus 32x. Okay, awesome. So far, so good. Now, I notice that there's something common I could factor out. Remember, the terms are anything separated by that plus sign or minus sign. So I notice that at the very least, both terms have this negative 4x squared minus 3. The front term has it and the back term has it. Now the front term has negative 4x squared minus 3 to the third. The back term has negative 4x squared minus 3 to the fourth. I can only factor out the smaller amount, so that's why I'm going to factor out the negative 4x squared minus 3 raised to the third. So here is me factoring that out in front of everything. So now my leftover terms become negative 96x to the fourth minus 32. That's all that's left right here after I take this part out. It's now out in front. I factored it out. Now in the back, once again, there was negative 4x squared minus 3 to the fourth. I was only able to factor 3 of them out, so that leaves 1 behind. So the 9x squared is still there, and then my negative 4x squared minus 3 to the first power is there. But now I could actually distribute that 9x squared because now I have this raised to the power of 1. So that's what I did in the back now. I simply distributed to get this top. Now let me go back and just show you that real quick. So inside I have a negative 96x to the fourth minus 32x. Then I distributed to get a negative 36x to the fourth and a negative 27x squared. And that is everything I got right in here. That is the entire inside. And then again, here is that negative 4x squared minus 3 cubed that I factored out. Then I was able to combine a couple like terms right here and right here. The negative 96x to the fourth and the negative 36x to the fourth made my negative 32x to the fourth minus the 27x squared minus the 32x. Then I just noticed one more really cool thing. All of these terms have an x that I could factor out. At the very minimum, they all have an x I could factor out. So I also factored that x out to the very, very front as well. So I was left with negative 132x cubed minus 27x minus 32. So there's my final answer. And again, the derivative part, I know this looks completely messy, but the derivative part was actually the easy part. It's all of the cleanup work, multiplying what I can, factoring out that expression, negative 4x squared minus 3 to the third, cleaning everything up after I factor that out, then realizing I can factor an x out, and that's what gives me my final answer. That's not extremely pretty, but it is my final best case simplified derivative. All right, that's a pretty tough one. Hope that all made sense. Now let's look at one that requires the quotient rule with the chain rule inside of it. So I clearly have my quotient rule needed here because I have something divided by something else. Now let me quickly remind you what the chain or the quotient rule is. You take the bottom, b, that's the denominator, you multiply by the derivative of a, minus, now you leave a alone, multiply by the derivative of b, all divided by b squared. So anytime you have a numerator, denominator, quotient rule is going to be very helpful. But when I do go right here to find the derivative of a, I am going to need the chain rule to find that derivative. All right, so let's dive into how I'm going to do this. All right, so first I'm leaving the bottom alone. There's the 3x to the fourth minus 2. Now I have to multiply by the derivative of that numerator. So the 5 falls down in front. Inside stays the same, x cubed plus 4, new powers of 4, and then multiplied by the derivative of the inside, which is 3x squared. All right, that's done. Now I'm subtracting. This time I'm going to leave the numerator alone. That is the x cubed plus 4 to the fifth. And I'm going to multiply by the derivative of the denominator, which is actually pretty easy. 4 falls down, 12x to the third. The derivative of negative 2 is 0, so I just get 12x to the third. And then don't forget the easiest part of all of this, dividing by the denominator all squared. So 3x to the fourth minus 2, all squared. Now, that's it. I am done using the derivative rules. Now all I have to do is clean it up, and that's what can get a little ugly. So first, similar to what we did with the product rule problem, I multiplied what I could. So let me go back here real quick and show you exactly what I'm talking about. So the 5 and the 3x squared makes a 15x squared. I'm allowed to multiply those. Then because this front value right here is raised to the first, I can distribute inside of that. So I can get a 45x to the 6 minus a 30x squared. I cannot distribute into this guy right here because he has that fourth power. Now in the back, once again, I cannot distribute because of the fifth power, so I just move the 12x cubed to the front, well, just because it makes it look a little nicer. So here's that 12x cubed that I moved to the front, and then the x cubed plus 4 to the fifth. That's my back term. My front term is, like I said, I took that 15x squared and I distributed it to the part that I could, giving me that 45x to the 6 minus 30x squared. And then here is that x cubed plus 4 to the 4th power. Then once again, I said, okay, what is common on top that I could factor out? And I actually saw that both terms, remember terms are anything separated by that beautiful minus sign right here. So I do have two terms, but both terms have that x cubed plus 4. X cubed plus 4. But I can only take out the smaller amounts. That's why I'm going to factor out an x cubed plus 4 to the 4th. That goes right out in front. So when I factored away from this first term, well, the only thing left is the 45x to the 6 minus 30x squared. Technically, didn't even need those parentheses around it. Minus, now when I factor out from the back, there were 5 of them. I'm only allowed to factor 4 out, so that leaves x cubed plus 4 to the first left behind. But now inside those brackets, I can now distribute this negative 12x cubed, which is going to get a negative 12x to the 6th and a negative 48x cubed. So that was my next step, was simply doing that multiplication. And then I have this inside portion right here that has a couple like terms. The 45x to the 6 and the negative 12x to the 6 can be combined. That's how I got 33x to the 6. Minus 48x cubed minus 30x squared. And then here is that portion that I factored out in front. And then, oh yeah, don't forget about that denominator, 3x plus 3x raised to the 4th minus 2 all squared. But then I realized one more thing. And to be honest, this isn't a terrible final answer. But I realized that between these three terms, I can actually factor out a common 3x squared. They all have a factor of a multiple of 3, and they also all have at least an x squared. So that's why I factored that 3x squared out in front, which left behind an 11x to the 4th, negative 16x, and a negative 10. So here is my, well, not so gorgeous final answer, but it is fairly nice and simplified, at least as best as I possibly can. All right, so those were some pretty tough problems that involve the use of the quotient product rules with the chain rules inside of them. Let's do another one that involves a square root. So here's another one with the chain rule, but quotient rule overall. So once again, I do have numerator A divided by denominator B, so I'm going to need my quotient rule. But when it comes time to find the derivative of B, I am going to need to use the chain rule. So let's start this process. Now, the first thing I will do is when I do use the chain rule, I really want to use power rule as part of it. So I'm going to write that 2x plus 5 to the 1/2 power. It's going to allow me to utilize the power rule through the chain rule. All right, so here I go. Let's take this nice and slow. I'm actually going to show you my work nice here. I know my handwriting can be a little bit sloppy, but I'll try to write nice. So I'm going to start with the bottom. The bottom is 2x plus 5 to the 1/2 times the derivative of the top, 3. Whew, okay, that was pretty easy. Not too bad. Minus, now I'm going to take the top, 3x, and I'm going to multiply it by the derivative of the bottom. But the derivative of the bottom is going to require the chain rule. The 1/2 falls down in front. 2x plus 5 raised to the negative 1/2 multiplied by the derivative of the inside. The derivative of that inside is just 2. So there is using the chain rule. And then again, I'm going to divide all of that by the denominator squared. Now, this is actually where something really cool happens. When I take the square root of 2x plus 5 and square it, I just get 2x plus 5. So that's kind of nice. All right, now comes all this fun cleanup work. And again, don't rush this. I highly recommend taking this in steps. All right, in this first term right here, really nothing I could do because of that 1/2 power. So I am just going to put the 3 out in front, 2x plus 5 raised to the 1/2. Minus, now back here there's a lot of different stuff I could do. The 3x, the 1/2, and the 2 can all multiply together. Well, 1/2 times 2, that's this 1/2 and this 2. That's going to make a 1. That's kind of cool. Times the 3x just makes a 3x. But then I still have the 2x plus 5 all to the negative 1/2. And I hate negative exponents, so I'm going to move that to denominator. So underneath the 3x, I'm going to create a 2x plus 5 all raised to the positive 1/2. Okay, but here's now the problem. Don't forget all of that is multiplied by 2x plus 5. All right, now there's a couple different things I could do to clean this up because this is going to get pretty ugly, but a couple different things I could do to make it a little bit nicer. So first, let's work with this numerator. This numerator is really ugly right now. So I'm going to treat this term as a fraction, putting it over 1, and then I'm actually going to combine those, getting a common denominator. So my common denominator is going to be 2x plus 5 raised to the 1/2, or the square root of 2x plus 5 if you want. Now, in order to create that common denominator, I need to multiply this by 2x plus 5 to the 1/2. But if I multiply the denominator, I also have to multiply the numerator. So this numerator right here also needs to be multiplied by 2x plus 5 raised to the 1/2. But something really cool is going to happen. Check this out. When 2x plus 5 raised to the 1/2 multiplies by another 2x plus 5 raised to the 1/2, the 1/2s turn into a 1. Now again, what actually happens is they're both square roots. And what happens when you multiply two identical square roots? The square root cancels and you just get 2x plus 5. But you could also look at it as when you multiply common bases, you add the powers. So the 2x plus 5 is my common base. Add the powers, 1/2 plus 1/2 is 1. So at the end of the day, I just get 3 times 2x plus 5 to the 1. Minus, now this back term right here, he or she, however you want to say it, already had the common denominator, so it needs no adjustment, so just minus 3x. And then don't forget to divide everything by the 2x plus 5. But I'm actually going to make that a little bit easier. Instead of dividing everything by this 2x plus 5 right here, I'm going to multiply by its reciprocal. So what is the reciprocal of 2x plus 5? Well, that should be easy. 1 over 2x plus 5. All right, now I'm really in for a really cool, somewhat pretty simple solution. Hear me out here. All right, so looking at that numerator, I can distribute this 3, 6x plus 5. The 6x and the negative 3x makes a 3x, so I get 3x plus 15. Excuse me, I said 5, I should have 15. 6x plus 15, but then the 6x and the negative 3x make a 3x plus 15. Multiplied by this 1 is just going to stay 3x plus 15. Now here's my favorite part. Check out this denominator. I have 2x plus 5 to the 1/2 times another 2x plus 5 to the first. But remember, when you have the same base, in this case 2x plus 5, you can add the exponents. So the 1/2 plus 1 makes 3/2. So in my denominator, I have 2x plus 5 to the 3/2. And that's actually not that ugly of an answer. 3x plus 15 all over 2x plus 5 raised to 3/2. Yikes. That's a tough one. I'm not going to lie. Maybe go back and watch that again. Process what I did. I know my handiwork is kind of messy a little bit, but it's actually not that bad. It all started off with simply using the derivative rules. Take the bottom times the derivative of the top. Take the top times the derivative of the bottom, which required the chain rule, all divided by the denominator squared, which kind of turned to a nice simple 2x plus 5. Then I just had a bunch of kind of ugly algebra to clean that up, but it works out really, really, really nice if you take your time. So probably want to practice some more problems like that. All right, let's do one more problem. This one's going to be where we have a quotient inside of a chain rule. It's almost opposite of what we just did. So here we actually need the chain rule first, and then we're going to need the quotient rule inside of that. So first, I'm actually going to rewrite this as 2x over x plus 1 all raised to the 1/2. So now you say, oh, okay, I guess I'm going to need the chain rule first to find this derivative. The 1/2 falls down in front. Inside stays the same. All raised to the negative 1/2. That is the one less than my old power of 1/2. Now here's where it gets a little tricky, because now I have to multiply by the derivative of the inside. But the inside is this, which is going to require the quotient rule. So here I go, finding the derivative of that inside portion. Denominator, left alone, times the derivative of the top 2, minus the top, 2x, times the derivative of the bottom, 1, all divided by my denominator, x plus 1 squared. Okay, that wasn't too bad. Now I'm going to clean that up a little bit, so let's see what I have here so far. I have a 1/2. And oh boy, okay, this is going to kind of get ugly because I don't like negative exponents. So I'm actually going to put that 2x over x plus 1 in my denominator where it could become a positive 1/2. So here's the 1 in my numerator, that's right there. Here's the 2 in my denominator, that's right there. And then I move the 2x over x plus 1 to the negative 1/2 to my denominator where it can have a positive 1/2. Ugh, that's kind of ugly, but bear with me. Now, what about the quotient rule? Kind of really some nice stuff happens here. I'm going to distribute this 2, and I get a 2x plus 2. And that's 1 times 2x, that's a negative 2x there because of the minus sign. And the 2x's are going to cancel, so that actually works out kind of nice. That's simply going to be a 2 over x plus 1 all squared. Okay, now I can multiply. Now, when you multiply, you do not need a common denominator, just multiply. So multiplying straight across the top, 1 times 2 is 2. Straight across the bottom, oh boy, okay, I have a 2 times the square root of 2x over x plus 1 times x plus 1 squared. Now, maybe I could make that a little bit prettier. Oh, wait a minute. How cool is this? These 2's can actually cancel, right? Because a 2 divided by 2 makes a 1. So I could make my numerator a 1. I mean, that's something a little bit better, right? Still not great, but better. And then in my denominator, I'm actually going to put the x plus 1 squared first, multiplied by the square root of the 2x over x plus 1. Now listen, that looks really ugly, and there is one more thing I could do to make that look slightly better. Just bear with me here, please. So let me come over here. So here's where I'm at. 1 over x plus 1 squared times the square root of 2x over x plus 1. Now, what I'm going to do is I'm going to get rid of the square root in denominators because that's kind of a rule. Like, we don't really love square roots in denominators. So I'm going to multiply both the top and the bottom by 2x over x plus 1 in a square root. So this is called rationalizing the denominator. Not very pretty, but check this out. Now, in my numerator, 1 times that is, well, the square root of 2x over x plus 1 is what it is. But in the denominator, something actually really cool is going to happen. When these two square roots that are identical multiply, I just get 2x over x plus 1, right? That's just the inside. That's kind of messy. Let me rewrite that a little bit. My handwriting's terrible. I'm working on it. So I have the 2x over x plus 1. But I also have that x plus 1 squared down there as well. Now that's kind of nice because now one of these x plus 1's will cancel with this x plus 1 in the denominator. So I get a square root of 2x over x plus 1 all divided by, now again, those x plus 1's canceled. At least one of them did. Again, one of these canceled with that one in the denominator. So all that's left is the 2x and then the x plus 1 as well. So again, where's that coming from? Well, here's the 2x. Here's the x plus 1 that didn't cancel. Remember, it's x plus 1 squared. One of them canceled. The other didn't. So there is my final answer. Listen, is it ugly? Yeah. Is it pretty? Not really. But hey, that is my derivative. So kind of an ugly problem, but that's the whole point of this video, is showing you how to find some tougher derivatives that are, well, kind of ugly. Sorry about it. All right, that's it. Hopefully you enjoyed this video. Hopefully these challenging problems made sense, because you never know. You might hit a couple of them every now and then. All right, thanks for watching. Don't forget to like.